To all, today we can discuss about the operation of enhancement MOSFET in the subject electron devices and circuits. So before going to the operation and working, first we can discuss about what is metal oxide semiconductor. So metal oxide field semiconductor field effect transistor is nothing but a field effect transistor with an insulated gate where the voltage determines the conductivity of the device that is mainly used for amplifying the signal. Now, in analog and digital circuits, MOSFETs are used more frequently as compared to BJTs because they are used in amplifiers because of their infinite input impedance. Okay, so this is the basic reason for going to MOSFET compared to the BJT. So the silicon dioxide forms the gate of the MOSFET, which provides isolation by preventing the direct flow of charges on the gate to the conducting material. So there are two types of MOSFETs. One is enhancement mode MOSFET and another one is depletion mode MOSFET. So this enhancement mode MOSFET is the mode of operation. The bias voltage on the gate increases the number of charge carriers in the channel and therefore increases the drain current. So in the depletion mode of operation, the bias voltage on the gate reduce the number of charge carriers in the channel and therefore reduce the drain current. So in the depletion mode, you have the drain current will be reduced, and in the enhancement mode, due to the application of bias voltage, that is bias voltage will be increased, that means positive, which will be increasing the drain current. So this both enhancement mode and depletion mode can act we have P channel and N channel. So how it should be N channel MOSFET? So in the N channel, the drain and source are heavily doped N plus region and the substrate is P type. The current flow is due to the flow of negatively charged electrons. That's the reason we are calling it should be an N-channel MOSFET. So this is the simple for N-channel MOSFET in enhancement mode as well as in the depletion mode. Enhancement mode, there will be some separation between drain source and gate because how it is represented is this particular between N plus and N plus, there is no channel. So here you don't have any channel, but if you see this diagram, here you have channel. So this represents is splitted here. There is no connection between drain and source. B represents the body. Okay, so actually, even though it looks like the 4 terminals, we are using only 3 terminals for operation. So in the P channel substrate, you see this P plus region is heavily doped. Drain and source are heavily doped. P plus region and substrate is in N type. The current flow is due to the flow of positively charged holes, and that's why we are calling it should be a P channel MOSFET. Okay. Next is the enhancement mode of working principle. So enhancement type of why it is considered, it is normally off, which means when an enhancement type MOSFET is connected, there will be no flow of current from the terminal drain to the source when no voltage is applied. So see here, you have it in the construction part, we can discuss. In the construction part, you see this, it consists of a P-type substrate. This one is the P-type substrate and two heavily doped N plus regions, which forms the source and drain, which is isolated from the gate. There is no there is no connection between the gate here. Okay. Next, the source and drain terminals are connected through metallic contacts. This is your metallic contacts, two N doped regions. But the enhancement MOSFET does not contain diffuse channel. Here there is no channel. This represents no channel between the source and drain. So this is the construction part of here. And the silicon dioxide layer, this metallization layer, here gate is insulated with the silicon dioxide layer. This is your silicon dioxide layer. And in between that, the gate is mounted. Okay, so this is about the construction of MOSFET. So it with the P-type substrate and the N-type substrate, a symbol diagram representing the metal electrode here. This is your contact. This is your silicon dioxide layer, and this is for N-type, and this is for P-type. Okay. How the construction? It has three layers, gate, drain, and source. As we have discussed, the body of the MOSFET is known as substrate that is connected internally to the source, and the silicon, whatever things which I have explained here is given in this PPT. We can discuss about the operation. but the drain is made positive with respect to source. So see this. First, we are not at all giving a drain. So first VGS, this is your VGS. VGS is 0 volt and then there is no channel that will connect the source and drain. The P-type substrate has only a small number of thermally produced minority charge carriers because free electrons are less in P-type substrate. Thus the drain current is 0. Okay, so the MOSFET will be normally off. But first you are going to apply the gate voltage that is positive. Then it attracts the minority charge carriers like electrons from P-type substrate, where these charge carriers will combine with the holes under the layer of silicon dioxide. So here it will be combining the holes with the silicon dioxide. This is a plus minus. It is shown here. Okay. So with respect, if you are applying a positive voltage to the gate with respect to the source and substrate, negative charge carriers are induced in the substrate. The negative charge carriers, which are the minority charge carriers in the p-type substrate, form an inversion layer. That is nothing but the induced layer. Okay. As the gate potential is increased more and more, negative charge carriers are induced. These negative carriers that are accumulated between source and drain constitute an N-type channel. The induced channel is of now an N-type channel. Thus, a drain current flows from source to drain through this induced channel. The magnitude of the drain current depends on the gate potential. Okay, so only because of this gate potential. Now, we are going to apply VDS between the drain and source, another one potential, that is VDS also. Okay, so now the conduction has begun. Now initially it is in off condition. Now it is going to the on condition and we are going to apply the next. So whenever we are increasing the further, it because the current flow start from this source to the drain. Whenever you are increasing this VDS also, once maximum level is reached, that is the saturation level, then the current flow will go to be a constant level. So once it is going to be a large level, after that it will be going to a constant level and the current drain current is simply proportional to the channel resistance, which will be depending on the depends further on the charge carriers attracted to the positive terminal of the, which makes the particular current to be constant. So how should be the characteristics? So there are two characteristics. One is drain characteristics, another one is transfer characteristics. The drain characteristics is also called as transconductance characteristics. The current, see this, it is having this there are several regions present. First is a resistance region or ohmic region, we can say, and after that it is going to constant, that is called as active region. And once the value is going to be beyond, it will be going to break down actually. This represents, this one will be going to be breakdown if it is exceeding that particular level. Okay, so when the VDS is increased further, it is going to be breakdown. So the plot between VDS versus ID for various values of VGS, it is shown. It is clear that the current ID will become constant at a specific value of VDS. The current ID increases only the value of VGS is increased. So the major one is VGS is increased and it is going to see this 10 volt, 9 volt, 8 volt. It is going to be, if the VGS is reduced, your current is going to be reduced. So the drain current increases with positive increase in gate source bias voltage, which is represented as drain characteristics. Next should be the transfer characteristics. So in the transfer characteristics, it requires a positive gate to source voltage for its operation. So VGS and ID, between the VGS and ID, you are going to plot this. Shows the characteristics. Since the drain current is 0 for VGS is equal to 0, the IDS is 0 initially for this device. So the first value is 0. The gate source voltage at which there is significant increase in the drain current is called this threshold voltage and it is referred as VT, or sometimes it is represented as VGS threshold. Okay. So the equation which relates this current ID and VGS is ID is equal to K into VGS minus VT. VT is nothing but the threshold voltage VGS TH the whole square, where constant K depends on the device physical characteristics, that is depending on the type of the material and as well as the silicon dioxide layer concentration. So that it is totally in the positive VGS region, start rising at VGS equal to the threshold value. So this is about the construction, operation, as well as the characteristics of the enhancement type of MOSFET.